Yeah, I know you're wondering like what's going on in this picture here. Um, it's like I know my room is haunted by Anne Boleyn. You know, Henry VIII's wife that got beheaded. Yeah, she I don't know how she got here from England, but yeah, she's been in my room. She's a benevolent ghost. Okay. Yeah. All right. Some people have the gift, like Ethan, they can see her. You know. Okay, so here we go. Evaluate each of the following. Yeah. Victory Japan Day? Yeah, it's the day that Japan surrendered on the U.S. Yeah. Yeah, is that right? Oh, well, I did announce. Okay, so it was interesting, and Ella and I have talked about this, but today's the day that World War II ended, and yesterday was the day that World War II started when Germany invaded Danzig, Poland. Right, I know. World War II was a one-day war. Yeah, that's kind of an interesting little factoid there. Of course, it started in 1939 and ended in 1945, but you know, right. Now, interesting note here. VJ in Japan is celebrated on September 1st, not September 2nd. So in their history books, World War II started and ended on the same day, which I guess is their way of saying we never lost. You know, it never happened. You know, wars only count if they're more than one day. It was a 6-year war. An L? I don't know. Maybe so. I don't know if they celebrate VJ Day in Japan. Probably not. Okay, I'm recording all this, so let's go. Yeah. Yeah. Maybe so, right? It makes you better. Your defeats make you better. But anyway, that was a terrible time, right? The greatest generation, they call those guys. All right, the limit as x goes to infinity. Notice this one's a little bit different because we have terms, and we have exponential terms. Oh boy. So remember, exponentials are the form b to the x. If the base is greater than 1, it's growth. And they have dramatically different end behaviors, right? On one end, they explode and get really, really, really big and dominate the growth. But on the other end, they go to what? 0 and become insignificant, right? That's important. They dominate and go to infinity on one end, or they go to 0 on the other. That makes these problems exceptional. Watch this. The limit as x goes to infinity. Remember, you don't want to plug in infinity right below there, but off to the side. 3 to the infinite power. What is that? Getting big or small? It's getting huge. So the numerator is approaching 8 minus infinity, which is what? Negative infinity, right? Negative infinity. And the denominator is approaching 4 plus infinity, which is positive infinity, right? Jeff Bezos has infinitely many dollars. You buy a $4 thing on Amazon, guess how many dollars he still has? Infinity, right? 4 plus infinity is infinity. Now, what is infinity over infinity? Is it 1 or negative 1? 0 over 0 is an indeterminate form. We know that that means that the limit exists, and the answer could be for the limit 5, 0, 12, whatever. Whatever the value of the whole is. Infinity over infinity is another one of the indeterminate forms, believe it or not. Because remember, how are infinity and 0 related? They're reciprocals. So if you reciprocate this number, you get 0 over 0. Infinity over infinity and 0 over 0 are reciprocals of each other. Okay, so this is an indeterminate form. But we can get the answer in this case because they both belong to the same family. If that were x cubed over x cubed, which is what we're used to, it would be leading coefficient over leading coefficient, right? Well, it's 3 to the x over 3 to the x. They grow at the exact same rate like x cubed and x cubed would. So guess what the answer is? Leading coefficient over leading coefficient. And the answer is negative 1. Yeah. Okay. Now, if that were 3 to the x over 4 to the x, now 4 to the x grows faster like x to the 4th would, right? And it goes to 0, okay? But A lot of the times these problems show up like this, where you have these constants and then these same powers or same bases of exponential growth. All right. So in this case, the 8 and the 4 are insignificant, right? The Jeff Bezos thing, everyone understood. The $4 purchase got absorbed into infinity like it wasn't even there. Okay, it was insignificant. Look at this one. You try this one on your own. Go. Keanu Reeves, man, what a nice guy. It's his birthday today. Happy birthday, Keanu, 56 years old. Nice guy, super nice guy. So I've heard. You got the same answer?
That's what I thought.
Oh, okay. All right. Well, that's okay. You're entitled to your answer, Ethan. How's your dog doing, by the way? I missed that girl.
Yeah, she's doing good.
Yeah, cute.
She might be at the store right now, although that's not.
Does she go by herself?
No.
No.
She is taken in by my father. Yeah, she wants.
I have the same kind of.
Really? A Goldie Doodle?
Yes.
Hey, let's plug in negative infinity off to the side, not below there, right? We already had this conversation. 3 to the negative infinity over 1 is the same as 1 over 3 to the infinity, yes? And what does that approach? If the top stays at 1 and the bottom gets huge, that approaches what? 0. It goes to 0, right? We're on the other end of the exponential growth functions. So now that we're going to negative infinity, this thing goes to 0, this thing goes to 0. And now the ratio is approaching 8 minus 0 over 4 plus 0, which is what? 8/4. Yep. That's what makes exponentials exciting. As you go out to the right, growth functions get huge and they overpower everything. But as you go to the left, exponential growth functions go to 0. And now the constants have their day. Yay, constants.
So why did that one do that?
I lost you?
Oh, you lost. Why did that one do that and the other one didn't do that?
Well, because I plugged in a negative infinity for x. What's 3 to the negative infinity? It's 1 over 3 to the infinity. So if I plug in, this term goes to 0. Yeah. Yeah, here's the graph of 3 to the x. It looks like this. Right? So as I go to negative infinity, this thing goes to 0. And so now they become increasingly insignificant. And 8 does not get absorbed, nor does 4. They stand out more prominently. Yeah. So that's what makes exponentials kind of cool, to kind of put into problems like this. It's not just leading coefficient over leading coefficient because they're going to 0, right? Does that kind of help now with the graph? You see the graph? But with infinity, remember, you can always plug in. You just have to kind of know what the trend is. Anything to the negative exponent power is the same as 1 over that positive power. And if the top stays at 1 and the bottom gets really big, 1 over 10, 1 over 100, 1 over 1,000,000, that's getting really small, approaching 0. Okay? Yes? Oh, yeah, so going back to that one, this one was positive infinity just because x to the x is the queen of growth. And it's going up against the king of growth, right? But the top still grows faster.
Well, I know.
For large x.
I get why it's not 0, but why is it not negative?
Oh, because we're going out to the right to positive infinity. Everything has been positive infinity. So all of our x values are positive. A positive number to a positive power is positive. And then positive factorial, we don't even really know what that means. But it's a positive number. Yeah. There's no negatives involved at all. Yeah. Well, that's a good question. Why infinity, not negative infinity? Okay. So you do have questions like example 7. They show up on the worksheet. I think they're as multiple choice questions. Just respect exponential growth functions because you don't want to get trapped into being on the wrong end of them, right? Yeah. Yes.
So is 2 and 8 maybe? Like,
on 2. Yeah, absolutely. Yeah. If you were to graph the function 8 minus 3 to the x over 4 plus 3 to the x, it would have 2 horizontal asymptotes. One at -1, y equals -1, and one at y equals 2. You know what? We have time. Let's graph it. Oh, Mason already has it graphed. Yeah. Hey, Oren, that's a great question. I don't think I've ever graphed these before, but you know, seeing is believing, as they say. I saw $1 million once, and I was like, "Yep, that exists in a magazine." That's where I saw it. Let's try it. Let's try it. I like this because alpha y equals 8 minus 3 caret x, 4 plus 3 to the x. If you hit zoom 6, I'm not sure it's going to help. There you go. Okay. So now you see it in action there, right? And I guess we can even do this, right? We can graph in y2, we can graph y equals -1, and then we can graph y equals 2 down here. Boom, boom, and you can see it kind of stays in between them. All right. Yeah, the table gets overflow error, and so that's tricking the calculator. It'll just like you twist someone's arm enough, and they'll say, "All right, I give up." Not really, but I do. Right? They never approach 2, nor do they ever approach -1. They get closer and closer, but you know the machines that we look at are finite machines, and so it can't give you an infinite string of 9s practically. You know, so yeah, there is overflow error. Yeah, great. Thank you. In all the years that I've been teaching that, Lauren, I've never graphed it. So that was kind of fun. All right. So respect everything, but exponentials we learned today, we got to be like, oh, okay, opposite end behavior is kind of cool at positive negativity. And the other thing that we are to be on the lookout for is when you have quotients of polynomials and either the numerator or the denominator have a what in it. How did we start the lesson today? Square root, a radical, right? Because you don't want to get caught in looking at the effective growth rate for the entire answer. The effective growth rate gives you the number, and then you plug a representative sign into the original to get the plus or minus sign. Yeah. Okay. All right. Any other questions? We'll stop right there if there's not. Yes, Mara?
It's on the notes.
Uh-huh.
So whenever we did that,
Yes.
so that's different than this. Right?
It's kind of the same result. It's the same result. We just look at it.
Do you not have to do, like, if there's a horizontal line, like, you don't have to make that the limit, you just do it.
Oh, well, okay. Let me address, this was good. Yeah. They were the same problem. Up here, I actually said the limit on part C, 3C, was positive infinity and negative infinity, and it is. It actually is. Down here, when I said the limit as x goes to infinity of h of x equals negative 2x minus 4, that's probably a misrepresentation. What I was trying to show there, and maybe instead of an equal sign, and I thought about it at the time, I wanted to put an arrow. I wanted to show that it becomes negative 2x minus 4. And now you can get the same results by plugging in your infinity if you want, right? Negative 2 times infinity is negative infinity. And then as you go out to the left, negative infinity, you get positive infinity. So you still get the same types of infinity. Yeah, thank you. Such fantastic questions. There are like questions that are like, hey, how do you do this? And then there's those really insightful questions where you have that cognitive dissonance and you need to get it resolved. Like you have that itchy feeling in your sinuses and you got to sneeze. I like that. All right.
How do you know whenever you're going to solve for a horizontal or a slant?
It depends on the degrees, right? There's 2 cases, remember, when you have the ratios of polynomials that you get horizontal. When the bottom grows faster, it's always y equals 0, always. When the degrees grow at the same rate, it's always leading coefficient over leading coefficient. Those are both horizontal asymptotes. The slant asymptote only occurs when the top is bigger by exactly 1 degree, okay? By exactly 1 degree. And then you do the long division. You could have something like x to the fourth plus blah, blah, blah over x squared plus blah, blah, blah. And that's going to go to infinity on both sides. If you looked at your end behavior model, you get y equals x squared. You can actually have quadratic asymptotes, believe it or not. You'd have a vertical asymptote here maybe, and the graph looks like this. And then it can look something like this. But we're not responsible for finding the equations of those. Just the slant asymptotes that are linear, we want to know how are they going to infinity along the line, okay? So it's like the Montessors, right? Yeah.
I'm impressed.
Oh, thank you,
I
thank
was
you.
impressed.
All right. All right, any other questions while the recorder's still going? All right. Now the rest of the period, have a good rest of the period.